So today we'd like to discuss the topic of vector fields, so line integrals over vector fields. Now what we have here is really an extension of what we talked about. We'll be doing this in 3D space, but note that you can do all of this in n-dimensional space as long as you have the patience to carry out all of the multiplications and the dot products and the parameterizations that will be required. Anyways, what we covered in the last video is consider that we have some continuous function of 3 variables, so it assigns some scalar value to each point in space, and then we draw a path through that space, and we call that path C. It goes from some A to some point A here to some point B here. What we can do is we can parameterize this curve as some function, some vector function actually, which we call R. So R is the distance between any point on the curve and the origin, and that can be modeled as some function of t. So we can take this curve from some arbitrary function of x, y, and z into some parameterization in terms of t, right? And then what we do is we integrate along this using the arc length formula for a differential element and integrating the function with respect to t. Now what we're going to do today is we're going to do something very similar, except the only difference is now instead of modeling our function as a continuous function fluid, really like a fluid for 3D space associating scalar values to every point in space, we're going to associate vector values to every point in space. So every point in space is now a vector, so we have a vector field here, and we're integrating along the line across this vector field. Now what's interesting is its application to physics. So you can consider the vector field as some sort of force field. So the vector represents a force, and we remember it's derived from some potential energy. So the force might be the gradient of some potential energy. If you remember, if we take the gradient of F, we might get some vector field, right? And so this we call the potential function, the gradient of the potential function. And we call this the force. This would be the force. So now you might know why that's called potential energy, because it's the potential function for the force field. Anyways, this is a bit of a digression. We can now move on to kind of discussing the line integral over a vector field, and we call this the work. So in physics, you call that the work. We'll get into the physical applications in the next section when we talk about the fundamental theorem for line integrals, but right now we're just kind of going to talk about line integrals over vector fields in general. So the definition that we have here is, say f is some continuous vector field on some curve C, and this curve C can be given by a parameterization vector function r of t, and t would be between some values a and b. Then we can say that the integral of f dot dr is equal to the integral from a to b of f of r of t dotted with r prime of t dt. Now this is very similar to the definition that we had in 3-dimensional space for continuous functions. The only difference here is we're carrying out a dot product between two vector functions. The force field with respect to the line parameterization dotted with the derivative of that line parameterization. Okay, let's try an example. Again, this seems very abstract. Let's try it out with an example. Let's try finding the integral for the vector function f is modeled by x, y, y, z, z, x. For the curve C, x equals t, y equals t squared, z equals t cubed for t between 0 and 1. I'm giving you the parameterization. I'm feeling nice today. Let's try modeling this and finding the line integral. So what we can deduce from here is we can form a vector function from this series of parametric equations. So you get r equals t squared, t cubed, right? So then we can take the derivative, get 1, 2t, 3t squared. Fairly trivial. Now we got to find our vector function in terms of t, or in terms of r of t. So we know that x, we have all of our equations here. So we have our equations for x, y, and z. So we're going to plug this back into x, because c is really modeled by r of t. So if we do f of r of t, well, we have x times y, so that's t times t squared. So for the first term, we get t cubed. Then we have y times z, so y times z is t squared times t cubed, that's t to the fifth. And then for the final term, zx, we've got x equals t, z equals t cubed, t times t cubed is t to the fourth, right? So now we have all of our pieces, right? Because we're finding the integral over the curve of f of r of t, and we have that now, times the derivative of the parameterization vector function, all with respect to t. So we have everything we need. We have this component, we have that component. So now we got to find the integral. So the integral of f dr is going to be the integral between 0 and 1. They already gave us our bounds for t. And then we got to do a dot product. So we've got t cubed, t fifth, t fourth, dotted with 1, 2t, 3t squared. So what we're going to do, we're going to multiply all the terms that are on the same level, and then we just add them. So we got t cubed times 1 is t cubed, so we put that there. We got t to the fifth times 2t, that's 2t to the sixth. Then we got t to the fourth times 3t squared, which is 3t to the sixth. Well, those are of the same order, so we've got 2t to the sixth plus 3t to the sixth, and that is 5t to the sixth. You don't need to combine the like terms, it doesn't matter, but I wanted to do that. Anyways, we integrate that between 0 and 1, again, very trivial. T cubed goes to 1/4 t to the fourth, so then that becomes 1/4, and then 5t to the sixth, you get 5/7 t to the seventh, or 5/7. So you add those both together, you get 27/28. That's a really simple example of how you do a line integral over a vector field. It's pretty easy to deal with. You can imagine doing this in physics, maybe given some electric fields over some curve. Gauss's law kind of models that to some extent, although you're really integrating over a surface. We'll get into that later. That's when you have a surface integral, so that's like the double integral counterpart of this. But you can kind of see where it's coming from. You have some sort of path that you want to integrate over any field, right? And that's also applicable to physics. So in the next video, we're going to introduce the fundamental theorem of line integrals, and we're really going to stress the connection to physics here, so the connection to work, potential, energy, and force. We'll talk about conservative forces that you can derive from potential functions. It'll be fun stuff. We'll get into that later. See you guys then.